This is Porterville College, Physics 104B, homework solutions for Chapter 17. The first one is number 19. What's the pressure of an ideal gas? 3.5 moles occupy 2 liters at negative 150 degrees Celsius. Be careful, we need to use the absolute Kelvin temperature scale. We're going to use the ideal gas law. Because it's given in terms of moles, we're going to use PV equals nRT, which has N as the number of moles. Solving for pressure, we get P equals nRT over V, and R is 8.314 joules per Kelvin mole. So we're going to make sure the units work out properly. We have 3.5 moles times 8.314 times 123 Kelvin is the temperature. We divide by 2 liters. However, for MKS units, we need this in cubic meters. So we're going to do the conversion down here that 2 liters is, we multiply by a cubic meter over 1,000 liters to get it in cubic meters. And the answer is 1.8 times 10 to the 6th pascals. Number 20, excuse me. Okay. Number 20 is also going to use the ideal gas law. We have a gas cylinder with the given volume. The supplier claims it contains 45 moles of argon. You measure its pressure to be 14 megapascals at room temperature. Did you get what you paid for? In other words, how many moles is really in it? So we're solving for N. We're going to use PV equals nRT. Solving for N equals PV over RT. So we measure the pressure, 14 times 10 to the 6th pascals, times the volume. It says 6.88 liters, but we're going to convert that to cubic meters, just as we did in the last problem. Excuse me. We're going to divide by R, the gas constant. We're going to divide by the temperature, which 20 degrees Celsius, we add 273 and it becomes 293 Kelvin. We do that and we get 40 moles. So the manufacturer claimed that it was 45 moles, so we are shorted by about 11%. The next problem, number 21. Two moles of an ideal gas at 250 Kelvin and pressure 1.5 atmospheres. What is the volume? Next question, now we change it so the pressure is 4 atmospheres. Gas volume drops to half its initial value. What is the new temperature? All right. So we have N, we have the initial temperature, we have the initial pressure. It says 1.5 atmosphere, but I want this in MKS units. So I'm going to multiply by the conversion that 1.013 times 10 to the 5th pascals is an atmosphere. And we should get 1.520 times 10 to the 5th pascals. Question A asks for the initial volume, and so I'm solving for V naught, given T naught and P naught. Using the ideal gas law, solving it for V, we get nRT over P, and I get 0.0274 cubic meters. I've converted that to liters, so it's 27 liters. Question B says the pressure changes to 4 atmospheres, so I'm calling this P1, 4 atmospheres. V1 is 1/2 the volume. And I've solved it this way, a technique that I've taught in class. If we start with PV equals nRT, let's put everything to the left of the equation that is changing and everything to the right that's constant. So PV will divide both sides by T. We have PV over T equals NR, or we'll just say PV over T equals constant. Now, since PV over T is constant, we can say the initial PV over T is equal to the final PV over T. P naught V naught over T naught equals P1 V1 over T1. The question asks for us to solve for the new temperature, so we'll say solving this for T1, we should get T1 equals T naught times P1 over P naught, V1 over V naught. And we plug in the values, 250 Kelvin times 4 atmospheres over 1.5 atmospheres. The substitution I'm making here is that the final volume is half the original volume. So instead of V1, I'll substitute in 1/2 V naught. That divides out with this V naught in the denominator, and you're left with 1/2. You should get an answer of 330 Kelvin. Number 26. It takes 200 joules to melt an 8-gram sample of one of the substances in table 17.1. What is that substance? We're looking at melting, so we're looking at a heat of transformation, particularly the heat of fusion. So we'll start with the equation Q equals mLF. We're solving for the heat of fusion, L sub F, equals Q over M. We've got 200 joules divided by 8 times 10 to the negative 3 kilograms. That gives us 25,000 joules per kilogram. You look up on the table, table 17.1 for the one that's closest to it, and you should see that that most closely matches lead. Number 31. You have exactly 1 liter of ethyl alcohol at room temperature. You put it in the refrigerator at 2 degrees Celsius. What is its new volume? We're looking at the volume contraction of a liquid. We'll use this equation, V equals V naught times 1 plus beta delta T. Plug in all the values. We have the initial volume is 1 liter, 1 plus, we look up the volume coefficient for ethyl alcohol, 75 times 10 to the negative 5 per Celsius degree. We're multiplying by the change in temperature. Final minus initial, that's 2 degrees Celsius minus 20 degrees Celsius. If you had converted to Kelvin, it would give you that same difference of negative 18 degrees, whether it's Celsius or Kelvin. Negative ensures that it's going to be 1 minus something, so we're going to have a volume contraction. And we're left with 0.9865 liters. Number 34. A single piece of welded steel railroad track 5,000 kilometers long. If the track were free to expand, how much would its length change if the entire track went from cold winter to a hot summer day? Alright, how much would it change? Meaning I'm looking for a delta L, looking for L minus L naught. So if we set it up this way, first we're going to use the length contraction equation, L equals L naught times 1 plus alpha delta T. And again, we're looking for the change in length. If you distribute this L naught times 1 plus L naught times alpha delta T, you get L naught plus L naught alpha delta T. And this L naught alpha delta T term is the delta L. That is the change. So really what we're looking for, I'm going to take this part right here. That's what we're solving for. So down here it's that delta L, the L naught alpha delta T. And we plug in the values. 5,000 kilometers times, for steel, 12 times 10 to the negative 6 per Kelvin, times the difference in temperature. We're going to do final minus initial, so 40 minus negative 25. That's a total change in temperature of plus 65. And we end up with 3.9 kilometer change. Number 36 is another question involving the ideal gas law. Helium balloon, given the volume, the temperature, the pressure, the balloon rises to where the pressure is different, the temperature is different. What is its volume when it reaches equilibrium at the new temperature? Okay, very similar to a previous problem in this set. I've written out all the facts given. Keep in mind we need a Kelvin temperature, so I've got T0 is 293 Kelvin, T1 263 Kelvin, P1, V1 is what we don't know. So we'll take PV equals nRT, put everything changing on the left, everything constant on the right, so we're left with, once again, PV over T equals constant. And then I can say pressure times volume over temperature final equals pressure times volume over temperature initial. And we're going to solve this algebraically for V1, giving us V1 equals V0 times P0 over P1 times T1 over T0. You plug in all those values and you should get 11 liters. Number 37, another problem with ideal gas law. A compressed air cylinder stands 100 centimeters tall and has internal diameter 20 centimeters. At room temperature, the pressure is 180 atmospheres. How many moles of air are in the cylinder? What volume would this air occupy at 1 atmosphere and room temperature? Okay, it's PV equals nRT, but we have to figure out what the volume is. So it's a cylinder. We're going to use the formula for volume of a cylinder, pi r squared times h. So if you think about a cylinder, pi r squared is the cross-sectional area of the circle times the height. Pi, the radius is 0.1 meters squared times 1 meter. So there we have pi times 10 to the negative 2 meters cubed. Pressure is 180 atmospheres, but we need that in pascals. So we're going to multiply by 1.013 times 10 to the 5th pascals per atmosphere. And temperature is 293 Kelvin. We can use those to figure out using PV equals nRT. N is PV over RT. You should get 235 moles. Then we're going to change it, solving for volume, with a new pressure of 1 atmosphere, which is 1.013 times 10 to the 5th pascals. And so it has been reduced down to 5.65 cubic meters. Number 37. Continued. Oh, okay, I'm sorry. Thought we were on to the next problem. Alternate solution to question B. Okay, this is just another way to do it. PV equals nRT. We're going to look at only the things that are changing, P and V. So we're going to, well, it's already solved with the changing things on the left. So we can just say PV equals, all these things on the right are constant, which means P1 V1 equals P0 V0. And we're going to solve for the new volume. So V1 equals V0 times P0 over P1, which means V1 equals the original volume, which you have to, we found that previously, times 180 atmospheres over 1 atmosphere. So the volume has been changed by a factor of 180. Okay, now to the next problem. Number 41. A stove burner supplies heat to a pan at the rate of 1500 watts. Remember, that's 1500 joules per second. How long will it take to boil away 1 kilogram of water once the water reaches its boiling temperature? All right, the water's already at 100 degrees. We're just looking at the heat of transformation. We recognize that power is going to be heat divided by time. Question is asking how much time, so let's change that, solve this for T. We have T equals Q over P, and if we're boiling, Q is going to be mass times the heat of vaporization, M times L sub V over P. Plug in the values. 1.1 kilogram times for water, it's 2257 times 10 to the 3rd joules per kilogram. The numerator here will give you how many joules are required. But then we divide by the power of 1500 joules per second, and we get 1655 seconds, which is about 27.5 minutes. Number 48. How much energy does it take to melt 10 kilograms of ice initially at negative 10 degrees Celsius? We have to break a problem like this into chronological stages. And each of those stages is either going to be a change in temperature or a change in phase. So I recommend you list them out. Stage number 1 is while it's ice, it goes from negative 10 degrees to 0 degrees Celsius. Once it gets to 0, it melts. And then it's over with, because the question is asking how much until it melts. So we'll say that the total heat is Q1 plus Q2. Q1, the taking ice, raising the temperature, is going to be M times the specific heat of ice times the change in temperature. And then Q2, we're going to add mass times the heat of fusion. If you want to, you can do as I did. I factored out M just to make it a little algebraically cleaner. And so what we have is the mass of 10 kilograms times specific heat of ice. Be careful, this is not liquid water. That has a specific heat of about twice this. It's ice. So it's 2050 joules per kilogram Kelvin times a change in temperature of 10 degrees Celsius. Plus the heat of fusion for water is 334,000 joules per Kelvin. Add those up and you get 3.5 million joules. Number 60. Number 60 takes a 2,000 milliliter cylinder filled with liquid at 350 Kelvin. When the liquid is cooled to 300 Kelvin, the cylinder is full to only the 1925 milliliter mark. Use table 17.2 to identify the liquid. So pretty neat experiment here. We can judge, taking a change in temperature, judge the change in volume and figure out what this liquid is. I write out the given facts: initial volume, final volume. It's not going to matter that it's in milliliters, so I won't need to convert that. Initial temperature, 350, final temperature. It's already in Kelvin, that's good. We know we need the volume expansion formula, V1 equals V0 times 1 plus beta delta T. We want to solve for beta, and then we'll look it up in the table and see what this matches. So solving this algebraically for beta, we get V1 over V0 minus 1 divided by delta T. Plug in all the values. Notice how the milliliters divide out, so we're left with just a ratio minus 1 divided by 300 minus 350. And it comes out to 7.5 times 10 to the negative 4 per Kelvin. And we look that up in the table, and we see that that is ethyl alcohol. All right. Next is number 66. Number 66 says, show that the coefficient of volume expansion of an ideal gas at constant pressure is the reciprocal of its Kelvin temperature. Okay? Show that beta equals 1 over T for an ideal gas at constant P. Alright, so we're going to plug in. Beta is just generally, if you look back in the chapter for what the equation, it's not an equation I gave you in class, but if you look at equation 17.6 in the book, it says beta is just generally the change in volume over initial volume over change in temperature. So delta V over delta T. We change this around, we'll say that's going to be 1 over V times delta V over delta T. We're going to turn that into small increments using the notation of calculus, and we're going to say that's going to be 1 over V times the rate of change, dV dt. Then we can say PV equals NKT, ideal gas law, solving for V. V is NKT over P. And then we're going to take the dV dt. So we're going to take the temperature derivative of this, and then we'll say dV dt is going to be NK over P. Now, we're going to say beta is, and remember up here we said that it's 1 over V dV dt. But now we've got an expression down here circled. These are the two key expressions that I have circled. We're going to plug in for what is dV dt. So it's going to be 1 over V times, and we'll plug in NK over P. And that's what I have here. So we have NK over, and notice in the denominators, PV, the ideal gas law is PV equals NKT. So I'm going to substitute for this PV, NKT. The n's divide out, the k's divide out, and there you have 1 over t. So just a little bit of algebra fun to end chapter 17 homework.